Good afternoon, honorable speakers, distinguished guests, ladies and gentlemen. Welcome to the second plenary session of the main event of International Seminar on Chemical Engineering Suhadi Reksawardoyo, known as STKSR, in conjunction with Symposium on Photocatalysis and Photocatalysis, known as Symphosis. I'm Fatur, student from Department of Chemical Engineering, Institute Teknologi Bandung. It is a great and valuable chance for me to be your master of ceremony in today's plenary session. On behalf of 2020 STKSR-Symphosis Committee, I would like to extend a very warm welcome to all of you. We appreciate you taking time of your busy schedules to join us today. First of all, I would like to thank our sponsor and supporter for helping this event to come true. The 2020 STKSR-Symphosis is sponsored by PT Energi Manajemen Indonesia Persero, Kurita Water and Environment Foundation, and PT Rekayasa Industri. This event is also supported by the ITB Chemical Engineering Alumni Association, Badan Kejuruan Kimia Persatuan Insinyur Indonesia, and the ITB Chemical Engineering Student Association. Next, I will convey the health and safety regulations in this pandemic condition. If you are outside the house, then you must use masks and other personal protective equipment. 2 participants must keep a distance of at least 1 meter from other people. Then I will read the participant rules during the event. Participant rules. 1. Participants are not allowed to turn on the mic and camera during the event. 2. Participants are only allowed to ask questions through the chat room in Zoom or YouTube from the beginning of presentation by speakers until the end of question and answer session. Next, I will introduce the profile of today's plenary session's moderator. This plenary session will be moderated by Dr. Insinyur Yogi Wibisono Budi, IPM. Dr. Budi is an associate professor in Chemical Engineering Department, Institute Teknologi Bandung. He is also the Vice Dean of Academic, Faculty of Industrial Technology, Institute Teknologi Bandung. His area of expertise are chemical reactor engineering and process intensification. Now, without further ado, I would like to invite Dr. Budi to begin the plenary session of today's event. Dr. Budi, the time is yours.
Okay, thank you, Fatur. Assalamualaikum warahmatullahi wabarakatuh. Excellencies, dear colleagues and friends, dear students, ladies and gentlemen, welcome again to International Seminar on Chemical Engineering Suhadi Reksawardoyo in conjunction with Symposium on Photocatalysis and Photocatalysis 2020, managed by Department of Chemical Engineering ITB. My name is Yogi Wibisono Budi, and I will be the chairman through the second plenary lecture today. I am so delighted to see all of you here, even in virtual, and eager to engage with circular economy issues concerning resource depletion and environment impairment. Most importantly, a system is built in which resources come in a cycle, thus eliminating waste produce and minimize resource exploitation. In this session, we have 3 plenary lectures that will be given by Professor Dr. Ing Jairi Jarumair Klemes, Mr. Kari Herlevi, and Professor Dr. Andris Stankiewicz. To begin with, please allow me to introduce to you all our first speaker, Professor Dr. Ing Jairi Jarumair Klemes. He is from Brno University of Technology, Czech Republic. Here we can see his brief curriculum vitae. So Professor Klemes, he is a founder and president for 24 years of Process Integration for Energy Saving and Pollution Reduction. He is also chairperson of Keep Working Party of European Federation of Chemical Engineering for 7 years. He holds Marie Curie chairs of excellence and highly cited researcher, top peer reviewer, and top handling editor. His area is process integrations, sustainable technologies, and renewable energy. Today, Professor Clemens will deliver a lecture on plastic materials for the future, lesson learned from COVID-19 pandemic. And as a rule, after his presentation, if anyone has any question, please write your question in the chat room. Professor Clemens, so now time is yours.
Good morning from the center of Europe. I am sorry I can't be with you alive as I am about 12,000 kilometers apart, and it also carries on many time zones. So what I'm going to talk today is plastics. The question is, are plastics material for the future? And also because the world is coming through huge pandemics of COVID-19, I would like to mention and analyze some early results related to COVID and plastics. I invited as a co-author my colleague from my spill laboratory, young lady Yivan Fan. She is a key researcher in our group. She originates not far from Indonesia, from Malaysia, but she came to study, and at the moment she is an important part of our research group. So where we are, this is the city of Brno in the Czech Republic in Europe. As Indonesia is quite far, I am presenting a map telling you where we are. It is really the center of Europe. Brno is about 100 kilometers north of Vienna, not far from Prague, Budapest, Berlin, Warsaw, Frankfurt, Munich, and so on. And we live in the European Union, which has got advantage and disadvantage of Schengen, which means we have no real border, which normally is a great advantage. However, in the time of COVID pandemics, it creates some problem. Anyway, Brno is a historical city, the capital of a historical country, Moravia. The Czech Republic consists of 3 historical cities, countries, the Czech part, Moravian and Silesian part. And the city is about 2,000 years old, but the first settlements were here about 6,000-7,000 years ago. And it's a city which is always among the top 50 in the world by the quality of the life. It is not big, but big enough to get number of universities, theaters, historical building, and some other interesting features. So I hope when pandemic is over, you will come, because we are organizing also a number of conferences. Another of my activities which I would like to present is Journal of Cleaner Production. This is a huge journal. It is one of the top 10 by size journals which Elsevier is publishing. It started more than 25 years ago as a humble journal with 2 issues per year. Now we've got usually much more than 30, reaching 40, and the number of papers this year already is over 30,000. I am happy to see any good papers. However, because of the size and high impact factor, we are able to publish only 10 to 15 top of the top papers, cream of the cream. This is the Journal of Cleaner Production Aims and Scope. As you can see, it's very multidisciplinary, but the major issue, you need to present something what has got some impact on the environment, but positive impact, cleaner, more sustainable, less waste, less emissions, and so on. So, because of journal grown so much up, we recently, you can see in August 2020, created four daughters journals, and one of them, of spin-off journal, is called Cleaner Engineering and Technology, and I've got the honor to be the editor-in-chief. And here I am very keen to invite also good papers. This is the journal which is open access, so everything what you published is available to everybody. However, it will be later paid for, but at the beginning it's a unique opportunity to publish for free. But of course it comes through very serious peer of procedure. It's revised, but you are welcome to try. And now we are coming to plastics. Plastics appeared about 50 years ago, and when they first appeared, it was a major breakthrough, because before we had to make everything from steel, paper, wood, glass, ceramics, different metals, and plastics suddenly came in and provide enormous opportunities. However, everything has got pros and cons, advantages and disadvantages. And plastics have got one problem, because they are very durable. When they are used and become waste, they can create a lot of problems. Here you've got two pictures from media showing how it looks when the waste of plastic is not treated properly. Up to recently, China was importing plastics and dealing with them. But about 2 years ago, China said enough is enough, and the big world problem started. What are advantages of plastics? They are versatile, flexible, very strong compared to weight, durable, hygienic, low cost, resistant to corrosion, lightweight, waterproof. However, some of those advantages create also disadvantages when plastic become waste. When they are highly durable, they can survive 100 years as waste because they are resistant to corrosion, unlike, for example, steel, metals, and other materials. They stay years, tens of years, hundreds of years. So, what is the problem? Recently, it became big media campaign. Plastic is an enemy, plastic is foe, and let's move back. For example, for cups, which we are using to drink coffee, tea, soft drinks, and others, move from plastics to paper. Well, we look for the credible data, and the credible data we found from the UK Royal Society of Chemistry. You can see always the source of information at the bottom of the slide. And what this assessment says: paper cup consumes 33 grams of wood per 1 cup, but 28% more oil, 36 times more chemicals, 580 times more of wastewater, produces a lot of more pollutants, emissions. And finally, at the end of the life, when it's incinerated, which is one way how to deal with the waste, which is more and more used in advanced countries, you can get from paper 20 megajoule per kilogram, but from polystyrene you can get 40. But paper cup is not only paper cup, because if you use pure paper for your tea, well, it's become degradable before you finish to drink your tea. It would melt in your hands. So what the paper cup has, it has got thin layer of plastics. But in that case, this waterproof plastics layer makes the cup not recyclable as a paper. So conclusion, just to move back to paper, it's not always the best solution and it has to be considered. Shopping bag. Shopping bag is some kind of tool which we are using every day. When we go for shopping, the supermarket, we usually get polyethylene paper bag, reusable, not woven, polypropylene bag, reusable polyethylene bag with 40% recycled content, just to mention few. Here you've got a mass for 100 pieces. And what happens? Well, as you can see, this simple polyethylene mass is just 6 kilograms. Paper is quite heavy. Now, non-renewable energy. Well, for one use, it's a paper bag, not the winner. What matters a lot is number of uses. If we can reuse the bag, we are considerably reducing the amount of emissions impact on the environment. And as you can see, the clear winner is on the right, this black one, which uses some recycled plastics. And when it's used 8 times, the impact on the environment is the lowest one. So look on the fresh water, which we need for paper bag. Look on the greenhouse emissions. Well, for one-use paper bag, they are not very good. So everything should be considered, everything should be quantified. And for quantification, it has been introduced a tool which is called footprints. And footprints are quantifying impact on the environment based on life cycle assessment. You probably know carbon footprint. We will talk about it later. But at the moment, what are the potential plastic substitutes for further research and analysis? You can see the table here. I haven't got enough time to read it item by item, but I assume that most of the audience can read. And you've got different products, you know, glass, pottery, ceramics, natural fibers, paper, rice husks and other organic waste, milk protein, natural rubber. And each of them has got a use, properties, but also it has got some health impact and environmental impact. So this is needed to study and deeply analyze before we are making some decisions. I mentioned that plastic is friend, but plastic waste is an enemy. And this is what we took from the website which is mentioned at the bottom in blue, how different countries are dealing with plastic waste. And regretfully, Africa and Southeast Asia, especially South, is not doing too well, because this dark blue, and this is where the potential for improvement is. What are impacts of plastics debris? You've got something which is reminding crosswords, and it tells you effects which were detected, not yet detected, for different levels of biological organization, starting from whole ecosystem and finishing at the bottom by subatomic particles. And what was detected, this left part is actually growing. It's not that it's totally harmless. It's that it's not yet detected. You know, it's a joke saying, can we be sure that we are absolutely healthy? And this joke said, you are never healthy. You are not properly diagnosed, because we don't know what are the potential health problems in our body. And this is similar with plastics. So another very important and unfortunately growing and dangerous issue are microplastics. Very small particles of plastics, because we can see plastic bags, we can see empty PET bottles, but microplastics, they start from 5 millimeters by definition, but ends with nanoplastics, and there are many. I've got here some examples. Fibers, pellet, cosmetics. Well, if you've got morning tea, and if you use this plastic tea bag, by making your tea, it released more than 1 million nanoplastics. In the bottle with the water, it releases some very, very small micro and nanoplastics in the water which you drink and to the environment. Well, it is not all, also tires. Tires on our cars, when we move the car, but especially when car is accelerating and braking, it releases microplastics. And recent studies are showing that those microplastics are more dangerous for our health in big cities, especially when it's a high concentration, than emissions. So what is the solution? Well, big publicity was about biodegradable plastics. But are they really degradable? They usually degrade into microplastics and create more problem. Okay, we can say, let's take a refuge in our house, in our room. But our room is still not safe from the point of microplastics, because it comes from clothes, beddings, carpets, curtains, even air condition. Because air condition, to be safe, you would need really to change or clean the filter every week. How frequently? Look in the mirror and say how frequently we are changing filters in our air conditioners. So this is another issue which we should consider. Impacts of microplastics on the left-hand side in red is what has been already found, diagnosed, and the impact is especially on seafood and fish. But even when on the right-hand side, there are some issues which have still no evidence, and microplastics can be treated by our body as fibers. It is not for sure, because when it comes to nanoplastics, it can come through our digestion, it can come through our lungs into bloodstream, and there are some studies suggesting that it has got impact on cancer and similar diseases. So watch and be careful. Impact pathway of plastics. The major reservoir of plastics and microplastics is the ocean. Because finally, when we released in a big city, it goes to sewage, it goes to rivers, it comes to ocean. Some studies are saying that at the moment in world oceans is same amount of fish and microplastics. But fish is unfortunately not growing in the amount and quantity because people are catching it for food, and fish is also dying by different diseases and pollution. But plastics and microplastics are growing, and there are impacts here: economic, physical, chemical impacts, and all of them should be considered. What to do with plastics recovery? As you can see, plastics, it's not one material. We've got many different type of materials. This is the problem because we called it plastics, but it's not like steel. Steel is not the same. It's carbon steel, stainless steel, but at the base it is steel. It is steel based on carbon. This is why I am not very happy when some media and even some researchers are calling carbon-less decarbonization. Because, for example, steel and plastics are based on sea. So our enemy is not sea, our enemy are CO2, carbon emissions. But back to plastics. You can see what you need to do and what you can do. There are mechanical ways, chemical, thermolysis, incineration, and there are many unit operations to deal with the plastic recovery. The bad news is plastic recovery needs investment because you need to get somehow to mechanically, chemically incinerate it to deal with this, but also it requires energy and it requires water. On the other hand, it's embodied energy in plastics. When we've got, say, 1 kilogram of plastics, we can get some energy back. If it is properly recycled, it can release energy, but if it ends in landfill or ocean, all this energy is lost. So let's consider it and try to make it as much as possible. There are some studies to convert plastic waste to hydrogen, which can serve as a clean fuel. But on the other hand, we need some energy, some hardware, some machinery, some chemicals to make it. So it's one option, but if you look here, heating plastic waste, for example, old tires, we need to heat it up to more than 800 degrees Celsius. Well, how to get this temperature? We need energy for it, and so on. So another issue which we should consider, we can't recycle plastics forever. This is the same like with many materials. In that case, actually steel is very good, glass is very good, but paper, we can't recycle paper forever because high quality paper needs to have long fibers. And by each recycling, the fibers are actually broken and shorter. So paper finally finishes as a toilet paper or tissues where short fiber is advantage. And something similar, it happens with plastics because plastics haven't got fiber, but the macromolecular material, and by each recycling we are decreasing those chains inside. So usually it's said the maximum is 15 times, but no, not all plastics are recyclable up to 15 times. And not all plastics are created equal. And coffee cups can actually be recycled because there are two materials there, which is a big problem for paper, for plastics. When we are using coating, there are two different plastics. So obviously there are candidates for incinerating. And this has to be studied. And if you look for very potential future research, consider and why and how we should probably plan our research strategy. What we have introduced is one issue called plastic waste footprint. And plastic waste footprint we defined as the net externality cost as a result of fulfilling the plastic demand at the place. And to make this a little bit complicated definition more approachable, we put a little picture here where we are starting with production, use, reuse if possible, and after there are different ways how to deal with the plastic waste. And the footprint is calculating all energy, all cost, all resources in, and also all out. If you want to know a little bit more about it, on the bottom is the reference to a recent paper. And now the last few minutes about COVID-19 pandemics. Well, we all know that it influenced most human activities, energy, water, ambient, production, transport, health, supply chain, waste treatments. But what about plastics? And obviously, it is increase in environmental footprints of healthcare. Well, hospitals and all healthcare requires more energy, disinfection, sterilization by steam, by high temperature, but also by spirits, ethanol, isopropanol. We need test kits, we need PPE, personal protection equipment as shield, masks, gowns, gloves, and all this is finally ending as a waste. And this is the picture which we took in February from WHO, World Health Organization. But from February it grown enormously. So just to give you an impression how many millions of masks, gowns, goggles, gloves, disinfection we need. It's enormous. And if you look here, the base of most of it are plastics. But what happens after medical waste disposal? We just took a few horrifying pictures, beaches of Hong Kong, streets of the UK. But this is not all. Unfortunately, people are not always responsible. So what are the major plastics in fighting the pandemics? Masks, respirators, you can see the pictures. But more and more it becomes to test kits, because testing is now massive. And it requires a lot of energy, a lot of plastics, and a lot of waste. Those are different types of plastics, what they are used for. Mostly, as you can see, they are used for packaging. But this medical part on the top left in light orange is growing. This is what we done when we wrote our paper in April. But now this pie chart is actually changing and the medicals are growing. Pandemics also brought a big requirement for packaging, because if we would like to get safe food, safe everything, we need to package it. And plastics are ideal for packaging, but you can see energy consumed for bags, energy consumed for other things. So the role of plastics is growing, but on the other hand, the problem is energy, materials, footprints. Biodegradable products are another problem. I haven't got time to go in detail, but you can look on it. And it's not a simple solution as it looks like, and we can consider it in details. Another problem of plastic recycling is that with pandemics, the price of crude oil and gas went down. And what it means, the price of new plastics is much lower, the half of recycled plastics. So we haven't got economic incentive for recycling. And this is really, really a problem. Virus. COVID-19. Those are some figures, how long it stays on surfaces. And this is one of, beside droplets, airborne virus, this is another problem. As you can see, the safest surface is copper. The virus survives only 4 hours. Plastics 2-3 days, which is not too good, but not too bad. But metal, other than copper, 5 days, wood 4 days, glass 5 days, ceramic. Well, we have to be careful. And what are the alternatives to plastic mask? It's cloth. Some people are using it, but efficiency is much, much lower. And good point is they are reusable. But to be safely reusable, we need to wash and iron, and again, it requires energy. So, impact on the environment. The beginning looked nice, you know, NO2 decrease in China, in tourist attractive cities like Venice, canals become clean, blue sky in India, and so on. But it was during the lockdown and not after. After it became big challenges, especially with the waste management. And what is the problem? The waste management should be dealt in a responsible way, because on the top, this blue, with lockdown, the waste amount went down, but medical waste and dangerous waste went up. So this slide shows what we should do with contaminated medical clinical waste. In hospital, it's more or less on the right hand side is very well organized and rehearsed, but the household, we've got more and more sick people at home. And if we just don't treat it properly, we can very much contribute to spread out of the disease. So what are the conclusions? Future personal protection equipment should be treated in environmentally sustainable measures. Resilient supply chain, diversity of solution, burdening footprint of reusing, waste sorting, and very important is response to waste management system. So I've got 30 minutes, so I'm coming to the end. More or less in parallel with your conference is a conference which we are organizing in Brno, in our city, which is online as well. So you still have got chance to register and listen pre-recorded presentation. This originally small conference grown to audience of 56 countries of the world. So it is something, and you can learn something. And next year, we would like to invite you again to Brno, to already 24th conference of process integration, modeling and optimization for energy saving and pollution reduction, which is going to be in 1 year time. And we do hope it will be face in face. But for some delegates who are far away, it will be also online option. Future conferences, I believe, will be hybrid. And this is the last slide. This is the slide which is acknowledging the funding which we've got for our research. Thank you very much to European Union and the Czech Republic Ministry Operation Program Research.
Okay, thank you very much for your interesting talk concerning plastic as a material for future as friend or enemy. And also you discuss the waste management that should be done in a proper way. Now, if anyone has questions, I'm sure Professor Clemens would be pleased to answer your questions.
Okay, I can read one.
Yeah, I think
which is saying, what's your suggestion to use in the developing countries packaging material due to our concern mostly on price or economic? Well, the money are always the king. We are talking about environment. Of course, we would like to live in clean environment, but if we like it or not, money matters. But the right solutions are the solutions which are economically viable, and it means cheaper. And packaging in the time of COVID-19 is a real issue. We consider that what is packed by plastic that is clean. Well, we can believe it or not, but this is the case. But it's no solution which would suit all. But my opinion is for packaging to use the plastics, which is fine, but the minimum, and to deal properly with the waste. Because if we are, say, food, I like, for example, very much durians. This is the food which is typical for Southeast Asia and tastes beautifully, but it smells. And, you can't bring it to the hotel and I can't bring it to Europe by the plane. But when it's packed, the smell is okay. So it must be packed, but packed with the minimum. If we packed it on a big plate which is made from plastics, and when we throw out everything immediately, it's a problem. Things like this you hardly can pack in paper. And as I shown, paper is sometimes not the most environmentally friendly. So my suggestion is use plastic, but treat it properly. I already mentioned biodegradable plastics. Well, it looks as a good solution, but it's not very much reusable. I've got, say, plastic bag, and I forgot it for a few weeks at home in the storage, and suddenly I realized that these biodegradable plastics degraded into microplastics and created a lot of waste. So biodegradable plastic should degrade completely. But what would happen if it is still somewhere used? And many parts of biodegradable plastics are coming through the period of microplastics. So we have always to look on waste plastics footprint and really not finish at the moment when we use it, but what is happening with the other part of the life chain. It means from the use to the grave. This is a quick attempt to answer.
Yes, okay. So for the second question, we can see here from Mr. Jonathan, one of the remarkable characteristics of plastic as a packaging material is its durability and its stability, making it easily reusable. And currently, there has been an increase of demand in biodegradable plastics, which reduces significantly said characteristic. What are your thoughts on biodegradables, both economically and environmentally?
Yeah, I think this question I already started to answer. That we need to look how it is biodegradable and with what stages it comes. You know, it's biodegradable doesn't mean that we've got say plastic bag and we come home and it suddenly disappear in decompose into say original material, carbon, oxygen, water, and so on. And biodegradable plastics has got is not only fully biodegradable because you've got usually some colors on it, you've got some treatment on it. So I am suggesting if we suggest biodegradable again to explore step by step all what is happening with biodegradable until so-called grave, until it decomposes to the original material. So, and I can see what is your suggestion regarding PPE, the plastic waste. In particular, medical mask, I mean how to treat to use medical mask that also contain plastics. Well, this is a good point, but so far during pandemic, we haven't got any reasonable way how to treat it. The most safer treatment at the moment is to incinerate it, and to incinerate at high temperatures. Because what the major concern is now is virus, and it's very nice to do something with plastic based respirators and masks, but if we would like to reuse it, it needs to be disinfected. And again, we need to calculate how much energy, how much disinfection, how much equipment we need for it. And you've seen that the plastic masks, they are used over the world now in billions, because well, many of us are now wearing plastic masks, but it's good and fully protective for 2, maximum 3 hours. What it means during the shift, you should probably use ideally 4 masks, one person every day. You should use another when you are moving from the place of your work to home. So a humble count is 10 masks or 10 respirators per person per day. Can you multiply this? Can you multiply this the population of Indonesia? You would get enormous mountains of this material. And what we should prevent just to throw it out or to finish in landfill, because you've seen that the virus is surviving quite a long time. But anyway, this is the item which is worth to future research. And I think big hospitals would very much appreciate some kind of hardware which would convert use respirators to brand new. But at the moment, it's a big challenge. Okay.
You still have one more question?
Yeah.
Yeah, from Megawati, yeah, Dr. Megawati.
Most definitely the candidate, and it's one more. Will the world be sustainable, or it's just a jargon? Well, I should direct you to the book which I serve as an editor. And the title of the book published by Elsevier is How to Measure Sustainability. Because everybody is talking about sustainability. But what is the sustainability? There are different interpretations of it. And we haven't got a single unit or units saying, sustainability is 2, sustainability is 5, sustainability is 12.5. It's actually complex set of problems. But single answer, if wealth is sustainable, it is. It is already a couple of billion of years, otherwise we wouldn't be here. But the question is sustainable in what shape? We don't want to change our countryside to deserts. We don't want to change our cities to places. This is proven that in megacities, the major issue is pollution. And the pollution is actually guilty for premature death of 5 to 10% of population of megacities, which is much worse than at the moment COVID-19. And people and governments are not mattering too much because those deaths are looking as more or less natural. And what is this pollution and major problem of sustainability? Those are emissions like NOxes, SOxes, VOCs, ozones, and especially PM, particle matters. And particle matters include microplastics as well. So it's a complex set of problems, and it has to be studied, and we should treat one after one issues which are making our environment and our life less sustainable. Would you share as a most efficient and easy process to degrade plastic that can be directly household waste on industrial scale? Well, good question. Again, if I know the answer, I wouldn't be lecturing here, but I would be somebody like Elon Musk or Bill Gates and sitting on private island. It's not easy. As I said, plastic is not one material. We've got classification which is growing. And the problem with plastics is we need to promote this classification. You can see it starts that on each piece of plastics should be some indication what class of plastics it is, because we can't treat all plastics the same. Well, we can actually by incinerating. But again, incinerating needs a special high temperature incineration, which is not allowing dioxins to be released. So I think the first step, which will increase the efficiency, is to separate, and to separate immediately after the use. And here are huge reserves. We've got in Europe now waste bins which are yellow, and they serve for plastics. But we are trying to do something for the environment. We put it in this waste bin or waste container, yellow, but finally it has got about 20 different plastics. So it has to be separated, and separation is not easy. So far, we haven't got any automatic separation on the robots. In many countries, this separation is done by prisoners, as it is not very, very pleasant job. You've got container belt where you've got plastics, and you should pick it up by hand and put in those separated bins. So when we've got separated, okay, we can get best treatments for each. But at the moment, the choice is mainly landfill or just countryside throwing out or incineration. This is a quick answer.
Okay, I'm very sorry due to the time limitation. I think we have to conclude our discussion session. And if anyone still have any question, please write in the chat room, and the organizing committee would kindly forward to Professor Clemens. Thank you very much, Professor Clemens. And as
thank you for your attention, and I would be happy to answer some other questions in writing.
Okay, thank you. And as a token of our appreciation for your time and valuable contribution, we kindly present a certificate for you. So
thank you very much.
You're welcome.
Most appreciated.
Okay. So once again, we sincerely thanks for your amazing lecture today. So we give applause to Professor Clemens. So thank you very much.
Thank you, Professor Clemens. Thank you.
Thank you. Thank you.
Thank you. Okay, our next speaker is Mr. Kari Harlevy. He is Project Director, Circular Economy Sitra, Finland. So here we can see his brief curriculum vitae.
Hello, can you hear me?
Yeah, hello.
Yes.
Yeah, okay. So let me introduce Mr. Harlevy. So Mr. Harlevy is a project director in circular economy from Sitra, the Finnish Innovation Fund. He is leading the circular economy area at Sitra and also responsible for a resource efficient economy area in Texas, Green Growth for Sustainable Future program, and also Texas Silicon Valley office. And his area of expertise is circular economy, fast growing clean tech firms, and also developing countries like BRIC. Today, Mr. Harlevy will talk about carbon neutral circular economy that protects biodiversity. To save the time, Mr. Harlevy, so the time is yours.
Thank you very much. It's a pleasure to be here, and greetings from Helsinki, Finland. And I'll share my screen here so you can see my presentation here. Hopefully you can see it now. Should be uploaded here in your system. Can you see it now?
Yes, it's clearly.
Very good.
Yeah.
Thank you. Perfect. So I lead the circular economy here at Sitra Finnish Innovation Fund, and I'll tell more about the circular economy activities that we have done here in Finland and elsewhere as well. Sitra is the gift from Finnish Parliament to 50-year-old Finland back in 1967. So we've been around already for some time, and in that sense, our mandate has been quite the same. We are the future house for Finland, and we have to make sure that Finland is top of the things that are important for the from the future. Sorry. So basically, we are independent future house under the Finnish Parliament, and we also use only the funded returns of our fund endowment capital for our activities. So really kind of making sure that it's a sustainable model also from the funding point of view. So very interesting organization. So kind of think, build, tank, and connect. So making also strategies, but also piloting them in the Finnish society. So in that sense, quite a unique organization. Our market capital is around 850 million euros, and we use only the, as said, the returns of the endowment capital, which is around 30 million euro per year, roughly. We have a staff of 150. And circular economy has been one of the key areas. And currently we are also looking very much now in the biodiversity aspects, and I'll come to that as well. We have been thinking about this question for some time. How do we guarantee a fair future for everyone if the only thing we know for sure is that everything will change? And I think this is very timely already this year as well, because of COVID, but of course for many other reasons as well. So it's a kind of challenging question that we need to try to answer. One of the obviously critical things is the crisis that we are facing, from the biodiversity loss to climate change and overconsumption of resources. And obviously these all are interconnected many ways, and we see that circular economy is one of the tools to mitigate climate change or biodiversity loss, and certainly it's about being smarter with resources and reducing the overconsumption of resources. So these are the kind of facts and figures that I think are easy to understand, that really the extraction and processing of materials and resources have the biggest impact in biodiversity, around 90%. And obviously, if we think about emissions, the picture is a bit the same, that 45% of climate emissions are really about making the products. And it doesn't look good if you think about the global material use. It is also very, very challenging currently, so more than double by 2060. When you think about the biodiversity loss that I mentioned, that we are in the kind of coming years focusing more and more, there's obviously a big threat. 1 million species are threatened by extinction, and really the GDP is very heavily dependent on nature and biodiversity many ways. And when you think about circular economy as a tool, there are different drivers behind it. They are land use change, obviously climate change, pollution, and really the natural resource use and exploitation, and obviously invasive species as well. But many ways from the circular economy point of view, the kind of first ones are obviously very important. There are of course opportunities here as well, and in that sense the threat is always a possibility as well. In many ways, but of course it's a very difficult situation, and it doesn't look good from the circular economy point of view either. Globally, only 9% of the materials are circulating according to circular economy. On the other hand, construction industry and built environment is responsible for about 50% of all raw material usages, and around 67% of CO2 emissions is connected to material usage. And especially you understand in Asia, of course, quite well that it's expected that about 75% of people will live in cities, and population will continue to grow. So this is actually kind of summarizes quite well the challenge when it comes to circular economy. We really need to get better usage of current existing materials, and in Europe still it's not the ideal situation either. Most of the materials are used only once, and we are not very good in occupancy rate of cars or offices, especially now. For sure, most of them are empty due to COVID as well. But there are many other examples from food and other sectors as well. So basically, from the Finnish point of view already, we are using like too much resources, and we are heavy utilizing resources here in Europe as well. And we need to go to the one planet approach here. And the circular economy potentially is one of the solutions. We are in Europe also in more or less linear economy, where we are pushing this to more to recycling economy, where we increase the recycling rates. There's a limits what you can do with that as well, as it's still the linear model of just extracting, making products and then wasting it, even though it could be recycled or used as an energy. But really need to maintain the value of materials in the society, and that's where the circular economy comes into the discussions. It's really about going to the services and really making sure that the product design is really done well, so we have longer lasting products. And the reason why we should focus more in the upstream activities, the design activities, is that most of the product-related environmental impacts are really determined during the design phase. As said, this is a big opportunity as well. There's a lot of businesses that are driving towards circular economy in Europe. Mostly, although I have to say that this is like a phenomenon that is also picking up speed elsewhere in North America. For example, I've been to Asia also many times, latest in Singapore, and I know that these are very much discussed over there as well. And I had a privilege to visit your country at the same time last year. So in circular economy, basically, there is obviously the opportunity side. Finnish government, as an example, is pushing circular economy quite heavily currently for the next 10 years, 15 years or so. European Commission has its circular economy action plan under the Green Growth Green Deal plan, and businesses, for example, Finland, the biggest companies, 1/4 are utilizing already circular economy one way or another in their strategies. From Citrus side, as I think to connect organization, we are focusing currently in providing tools for fair and just transition to circular economy. So we are analyzing, for example, how jobs are changing within kind of this transition that we are having from fossil to more sustainable models. And we are also working with industries to help them to understand how they can change their business models towards a circular economy. We are working with digitalization effects. We know that digitalization is a very good tool for many things, including obviously remote webinars, but there is of course also the negative side that we have to understand the full picture of the emissions, for example, of digitalization. Then there is the global aspects that we are working. We are working, for example, in Africa currently with African Development Bank and our Foreign Office, and providing kind of insight about kind of continental level transition to circular economy. If I just cover the main elements that I see that are relevant for shift towards circular economy, there are 4 different stakeholders that has to be considered. First one is central government, and there's obviously the need for improvement of collaboration between ministries and public sector, but also private-public partnership models we are lacking in many countries. Municipalities and cities are very important. They provide a platform for innovation for companies as well, and obviously a kind of entry point for customers and to citizens as well. One thing that is quite recent from our side, we have published a guidebook how to make a national roadmap. And I know that in your country, you have been thinking of making one. So happy to share information later on about this tool as well. It's online and you can download it from there. But in a nutshell, it provides a process, kind of how to consider all the relevant things when you are making a national strategy for circular economy. and hopefully also some inspirational examples from Finland as well. But in short, the guidebook in a national level really stresses the things that the countries have to, of course, make their own roadmap. So there's no other country who can tell you how to do it, but certainly there are common points here. Collaboration is really necessary to get the wide understanding from not only from citizens and public sector, but really making sure that in the industries and the industry strategies and this kind of export part is also included. The strategies need to be flexible. We know obviously from this year's example already that they can't be very rigid. They have to be agile, and obviously every country has their own situational picture. And that's a kind of starting point for any vision, goals, etc. And obviously for monitoring and measuring success. And certainly when you decide to go and make a roadmap, you have to invest in execution, because in many countries you might get the strategy, but there's no good plan for execution. There are, of course, many things the governments can do in Europe. Of course, those countries that are part of EU, they have a good kind of internal market and also kind of ways to improve holistically a circular economy. But individual countries can do their own part as well. And there are many things you can consider, from taxation to boosting digital solutions and R&D, and obviously waste regulation is part of this, and recycling, but certainly from our point of view, not the most important. But especially experiments and pilots are important so that you get things ongoing on the ground. I could touch base the municipalities as one angle, and just shortly, due to interest of time, I'm not going to go in detail here, but one of the key things here is the municipality city level understanding of circular economy. For example, Mexico City has as a mega city circular economy plan. London it has made one, and Amsterdam. So there are good examples from different countries as well. But you need to have the bottom up as well, residents' awareness and education on circular economy, and obviously everything in between. But certainly top-down commitment is really important as well. And just to showcase that it's really not about single policy or anything like that. It's really about connecting different players. If it's like city bikes to go beyond the kind of usual transportation by car, it really means that you have to engage with different stakeholders to make the change happen, from manufacturers to repairers to the city residents, etc. So it's really a multi-stakeholder activity in that sense. So basically, I have covered the kind of national and the kind of municipality level. Businesses is something that I can't stress enough. They are agile, and they can pick up many things quite fast. And obviously, you need to have the markets that's done partly by the regulation, but then you have to have those who kind of make it happen, they're the enterprises and obviously citizens as kind of not only customers or consumers, but really innovators in a way that they also demand more and more different type of solutions. At least in Nordics, they are quite well on top of the trends and are demanding customers in that sense. From Citrus side, if you're interested more of our work in the business sector, I recommend you to have a look of our webpage. There's the most interesting company list, where we have compiled interesting business cases from Finland, 130 or so, and we are updating this list next year, most likely. So it really gives a flavor of what kind of businesses there are and what's their speciality when it comes to circular economy. It really is something like product life extension, which is quite easy to understand, but also to different kind of sharing platforms. And certainly replacing plastic is one thing that the Finns are targeting quite a lot, as we have a lot of companies from the circular bioeconomy. Those were Finnish cases, but if you're interested more about what's happening globally, this autumn we had a World Circular Economy Forum online, where we had 4,000 participants from 130 countries. And here we also presented some globally interesting cases. And they are obviously all on our website as well. And really from different continents, so you get a flavor of what's going on internationally. As a kind of finishing note, where we are now in Finland, so we have the highest number of circular economy programs and courses in higher education in the world. We are building on the Finnish education system, but this is of course a work in progress. So we are not there yet. We have to make sure that this is not only like a separate circular economy courses, but really integrated in mathematics and kind of manufacturing and whatever kind of education. So not like silo courses themselves. Finnish businesses, as I said, are interested in this and are implementing these models, and certainly Finnish citizens are very much involved. They see this is the only way forward. So obviously everyone's actions matter, and we need to push forward with circular economy, and certainly I'm happy to answer any question as I see that my time is coming up. But this was my presentation, and happy to answer any questions. Thank you very much.
Thank you.
Okay, thank you very much for your interesting talk. So now, if anyone has any question, I believe Mr.
Yeah, I already typed my question.
Yeah, I think the first question is from Professor Clemens. So as we can see here that the circular economy has a lot of challenges as being financial viable, but the main issues is CA should not be an ultimate target. It should be the minimum environmental footprints, which is to minimize the impact to environment. Okay, please, Mr. Hadovi.
Yes, I fully agree. That's exactly the point. Circular economy is not the end goal. As I mentioned in the early part of the presentation, it's really a tool to mitigate climate change and definitely the biodiversity loss and the impact there. So fully agree with Jiri. Thank you for the comment.
Okay, and then for the next question is from Professor Sitompul. So he has two questions. The first question is why you just focus on C neutral for biodiversity? How about the metal neutral, SE neutral, etc.?
Well, this is of course not like a statement that we are focusing only one thing. It's certainly we are working with many fields in Sitra as well. We are not a research organization ourselves. We are like a think tank, and we apply a lot of research from elsewhere and try to kind of combine them in also novel ways. So it's not a statement that we are not working with, for example, metals. So there's, for example, Academy of Finland that is currently planning to finance circular economy aspects regarding metals and they're kind of maintaining them in the society, especially in the city. It's very interesting work as well.
Okay, and then the next question is thermodynamically, the total entropy will be positive. Can we achieve the minimum total entropy for the world peace on CE?
Unfortunately, I'm not that kind of expert that I could really cover this question. So it's for the scientist, I would say to and maybe in this audience, as I see that there is quite a lot of experts. Maybe this is something that you can think during this conference.
Well, if I can try to answer this question,
Yeah, please.
I
Kiri,
think
please.
this is a very good question, because total entropy will be positive, and in that case, we should take the questions not from administrative point of view, but from the scientific point of view. And I believe that many administrators are not scientists, but they should bring scientists to the team, as this is very, very important.
Any comment, Mr. Herlvi?
I agree with Professor Clemens. I think there is not enough collaboration between scientists and policymakers. I'm not a policymaker either, so I can only state what I have seen so far. So definitely there is a need for that kind of collaboration, but also kind of maybe more like bridging the scientific kind of results with more easily understandable format, where also policymakers could actually formulate policies, because they are not usually easily transferable. And in that sense, there is like a need also a bit of like clarity in between. Obviously, scientific results themselves are important, and there are different kind of ways to utilize them. But for the policymakers, I've seen that they need to be like also some recommendations, and maybe going a bit further from the science, and try to kind of suggest also how policymaker could actually implement some of the findings.
Yeah, I put in the chat the reference to the book. Yes. I was discussing. If you want to learn a little bit more, you can look in it. Thank you.
Okay, thank you very much, Professor Clemens, for sharing the information regarding, I think this is a book, yeah? Yeah. Okay, we still have another questions from Professor Setiadi. Could you give an example of a developing country is moving forward to the application of CE?
That's a very good question, and very timely currently. Of course, I know a bit of the situation globally, but not like a full level. What I've seen, especially through our work in Africa with the African Development Bank, there at least there is an interest for circular economy, but it's more about waste management approaches. They are important, of course, as there is big problems in that field, but most of the developing country approaches are about making sure that they can better recycle and better use the kind of resources they have. But that's an important part. But we also see there's an opportunity for, maybe the word leapfrogging is not the best here, but also to innovate and find ways that go beyond traditional recycling and waste management. And in Africa, for example, there are obviously examples from other sectors where, for example, use of mobile phones and payment systems, etc., have kind of been interesting from the innovation point of view. And I would set my eyes, especially in some of the African countries, especially those that have joined the African Circular Economy Alliance. there are countries like Rwanda and Nigeria and South Africa, to name some that are actively part of that group. And elsewhere, it's maybe a bit harder to name some of the interesting countries. In Latin America, for example, Colombia has a very ambitious circular economy strategy, and the challenge is the implementation of it. I don't know exactly how it's going forward, but certainly the ambition level is right. In Asia, you more or less, I'm sure, know better than I do what is the situation there, but happy to talk of that as well. Thank you.
Okay, we still have one more question. So from Mr. Owen. So this is from YouTube, I think. The circular economy aims to eliminate waste and implement continuous usage of resources. Does this mean that circular economy will require changes in consumer behavior? If yes, how should a company act if consumer deny the changes required?
I didn't see the question, so what was the last part of it? How consumers?
Yeah, how I think the consumer should, how should a company act if consumer deny the changes?
Right. Yeah, it's a not easy part, and also here in Finland, it's not evident that what, for example, citizens say and what they do, that there is alignment. And I think that's most likely in many other countries as well. There is, at least in Nordics, a strong appreciation for environmental topics, but then the actions are not there yet. People haven't, for example, tested sharing models and these new approaches that much, and indicating that there is not like a fast change happening, at least in the Finnish context. When it comes to companies that are providing these kind of new services and kind of products based on circularity, like in EU, there's a target by 2030 that all products should be done with circular economy principles, which is like a very big challenge. That it is helpful if there is regulation that supports this. But if there isn't, then it's really depending how the customers are valuing, appreciating the new products. And if they aren't, that's of course very difficult. Educating is one way, but it's a long road and expensive road, and most likely it doesn't lead to good profitability, especially if there's a long way to go with the kind of customer enlightenment in a sense. One way is to focus on those markets that are front runners and try to build the business first there. And that's at least what I would do from the circular point of view.
Okay, thank you very much. So another question. So we can see here from Jonathan. Circular economy implementation requires huge investment and intensive research and development on products. This is challenging to implement, especially in developing economies, where practices such as land use change and fossil fuel uses are vital to the expanding economy. How far do you think should a nation prioritize sustainability over increasing the prosperity of the people through economic growth?
So is the question here, in a nutshell, that in growing economy, relying on kind of consumption, what are the ways to build circular economy? What was it so? At the moment I can't see the questions here.
So I think I'm trying to get the question from Jonathan, but in most of the developing countries, they are depending on the resources, so that how a nation or a government prioritize within the sustainability and then economic growth. So that one is part how the balances of that. Probably you have could address
thanks
that one.
Yeah, it's a very good question, and it's not only the developing countries. It's, I think, every country. Obviously, there are big differences, but the main idea there is the same, that how to build the welfare. At least in Finland and many Nordic countries, it's about welfare, and we are maybe in that level that it's easier to discuss about that the decoupling of welfare from the economic growth. Certainly, it's very difficult, if not even possible, to decouple growth from material use, and in that sense, many countries, and especially developing countries that are in that kind of growing phase, face this dilemma. And I would say that there is no easy answer here in that sense. Investments are needed, more or less, and even in developed countries, you need to have investments in place in order to get climate-friendly solutions. And it's not like we can have degrowth or something like that. So it's really about investments, but it's really also to shift those investments. I think China has been quite interesting. The model, of course, I'm not a specialist in any countries in Asia, but certainly, at least to my understanding, they are trying to kind of shift heavily to renewable energy, and the circular economy has been in the agenda for 10 years or so. So it's interesting to see, is it possible in that scale? But it is a challenge for smaller countries as well, which are relying on exports, for example. So it's certainly a dilemma there. But the main challenge, I think, in many countries is that they are not able to, for example, make targets of how much natural resources they are willing to use, as it's not an endless resource. Could there be targets like that, which would maybe direct investments and innovation to be smarter with the materials, and having more value-added products and services? But that's a long road.
Okay, thank you very much. I think due to the time limitation, we have to conclude our discussion session. And if anyone still have any question, please write in the chat room, and our organizing committee would kindly forward to Mr. Herlvi. As a token of our appreciation for your time and valuable contribution, we kindly present a certificate for you. So here is the certificate for Mr. Herlvi.
Thank you very much.
Thank you.
Thank you very much.
Thank you.
Thanks. Bye-bye.
Bye-bye. Thank you very much.
Again, we sincerely thanks for your amazing lecture today. Thank you very much. And we give applause to Mr. Herlvi.
Thank you.
Okay, our next speaker is Professor Dr. Andris Stankiewicz, founder and chairman of the board of the European Process Intensification Center. So here we can see the CV of Professor Stankiewicz. So Professor Stankiewicz from Delft University of Technology. He is founder of the Working Party on Process Intensification at the European Federation of Chemical Engineering, and also board of European Process Intensification Center, editor of Elsevier journal, Chemical Engineering and Process Intensification, and also as a series editor of the Green Chemistry book series. His area, his research expertise is process intensification, chemical reaction engineering, and also industrial catalysis. Okay, so today Professor Stankiewicz will deliver a lecture on process intensification and advanced materials. So to save the time, Prof. Stankiewicz, so the time is yours.
Okay, thank you very much. Good afternoon, good morning, everyone. I don't know which parts of the world all of you are. Anyway, I'm in the part that is quite early and still a little bit dark here.
Yes.
But you know, in those gloomy and strange times, the technological advancement can make wonders and let the science still function in those times. So thank you very much for inviting me to this online conference. As you may know, first of all, I will try to share my screen with you to see whether it works. Let me see, share screen. Yeah, I'd like to share the screen. All right. And now I'm trying to, the PowerPoint. Okay. Is that okay with you? Can you see the screen? And
Yes. I can see well.
all right. Okay then. So yeah, as some of you know, I have retired recently from Delft. About the last 20 or so years, more than 20 years, my hobby was process intensification. So my talk today will be about process intensification, in particular, its relation to advanced materials. So what is actually the issue? When we look at first at the history of process intensification kind of timeline, it started around 1970, but the real acceleration came already in this millennium. And there are many initiatives. Professor Wibisono was kind enough to mention this European Process Intensification Center, the Working Party. Also in the United States, we have this Rapid Institute for Process Intensification, Modularization. So there is a lot of things happening. There are books printed, there are journals published, a lot of things happening. When you look into how we started with process intensification, it was in the year 2000. We have been invited by Chemical Engineering Progress, the American journal, to write a paper for a kind of special millennium issue of the journal. And Professor Moulijn, my colleague from Delft, and myself wrote a paper on process intensification transforming chemical engineering. And it was quite an important paper, as appeared later. It's got almost 1,000 quotations so far. But the most important thing is that we introduced somehow a structure to process intensification. We said, you know, process intensification is a kind of toolbox. And in the toolbox, you see equipment, the hardware part, and also the methods. And that we categorized the methods and the equipment. We brought some examples. And this approach to process intensification has functioned for many years, and it functions still. But obviously, at a certain point, a question came. And the question is, how about materials? Because we were talking about equipment, we were talking about methods, but materials were mentioned only real occasionally. There was no systematic analysis on the role of materials in process intensification. And when you look into the history of materials, obviously you see very old papers coming from Industrial Engineering Chemistry Journal, 1932. These were basically materials used for constructing chemical equipment. So constructional materials used in chemical engineering operations. After the war, the same journal has issued a special issue only on materials of construction, and still there were only materials for making equipment there. Now, let us look how chemical engineering has changed through the years. So I'm coming back with this slide. I'm coming back to the year 1977. This is the year I graduated from Warsaw University of Technology as a master's student. And I bring here some headlines from the same paper, from the same journal, the Chemical Engineering Progress, the headlines as they were in 1977 and the headlines as they are now. Look at them. 1977, boilers, burners, filters, fluidized beds, distillation things, filtration, tower packings, fin tubes. Look what happened here. Hydrogels, laser materials, coatings, polymers, living materials, silicone materials, glues that stick wet, when wet, aerogels, and so forth. You see that the focus of our discipline has moved clearly towards materials. So now is the question, obviously, what these materials can mean for process intensification. And I will be bringing some examples looking at functionalities of the materials, so of the properties of the materials and what they can offer to us. So first of all, let us look at the materials that can intensify catalytic reactions. A few examples here. First one, we will talk about structural shape and selectivity. And here, very important, but very well known already, metal organic frameworks. This is a hot topic today. And you see here some examples how alkylation reactions can be changed, can be modified by using the MOFs of special types. So we can very clearly and drastically change the selectivity of the reaction using MOFs. Another property, pore size structure, carbon nanotubes. You see here two examples of carbon nanotubes that were used for methanol synthesis from CO, and you see here very, very high conversions and formation rates due to the use of this material as a catalyst support. Also here in this paper, you see 50% higher conversion and more than 60% higher selectivity. Let's look at the other material that also offers pore size structure. This is development coming from UCL, University College London, where in a group of Professor Marc-Olivier Coppens, they developed a sponge-like architecture material. This is silico-aluminous phosphate supported catalyst. And again, in isomerization, hydroisomerization of 1-heptane, you see 2 times higher isomer yield due to this particular property of the material. Now, selective permeability, this is the world of membranes, obviously, and the example that I want to bring here is the palladium alloys membranes. This is a paper published by the group of Enrico Drioli from Italy, a very well-known scholar in membranes technology. You see here the water gas shift process done conventionally and done with the membrane, with the palladium alloy membrane. What they claim here is 2 times higher CO conversion in 9% of conventional reaction volume. So you can kind of shrink the process and get a better conversion due to this alloy material of the membrane. Another is a property that you can think of utilizing this to intensify processes, enhanced absorption capacity. You see here graphene oxide supported catalyst. Again, the methanol synthesis, almost 40% higher space-time yield when using the nanosheets of graphene oxide as a support for the catalyst. Super wettability, that's another story. You can think also of this property that can intensify processes, and a wonderful example here is the one of a hydrophilic TS1 zeolite, hydrophilic one, when compared to standard TS1 zeolite, this hydrophilic form of it proved to deliver 8 times higher reaction rate in the oxidation of 1-hexane with hydrogen peroxide. So really amazing improvement. Responsiveness to dielectric heating. So in other words, microwaves. We know that microwaves can be used to speed up processes. And this is a chitosan supported palladium catalyst that is reacting to microwaves, is picking up the microwaves energy. And in this case, Suzuki reaction was increased, the rate was increased around 12 times for reaching the same conversion. So microwaves, but also induction heating. We have materials that react to induction heating. Obviously, they get heated very quickly. Induction heating is by far the fastest method to heat materials. It's order of magnitude faster than an open flame when you compare those. So you see here silica-coated manganese nanoparticles, manganese ferrite nanoparticles. And again, a reaction was hydrogenation of alkene. And the reaction time, you see, from 10 hours to 8 minutes reduction. Amazing result. Now let's move to from catalytic process. Let's move to a mass transfer. So can advanced materials intensify mass transfer? And obviously they can. For instance, when we look at the property that is molecular sieving, you see again the MOFs, and MOFs are very known for instance, for selective absorption properties. And here you see complete exclusion of propane from propylene. If you compare it with a distillative separation of those two, propane from propylene, the projection is that you can spare about 80% energy. And there are two papers in Science on that. Capillary reaction and porosity of the material is also important. You see here silicon carbide foam. Silicon carbide foam used as a tray in distillation tower. The tray efficiency is claimed to be 60% higher than in the conventional sieve tray in that case. The same material property characterizes carbon foam Raschig rings that were investigated as a packing material for distillation systems, and they were compared to metal Raschig rings. And as you see, 30% lower HETP, up to 40% lower pressure drop, 20% higher flooding point. All the advantages just coming from the fact that you exchange the standard type of material into the foam, carbon foam. Right, responsiveness to magnetic field. This is something that occurs in biological separations or biotechnology in general. You can think of cell recovery by using magnetic nanoparticles, and the idea is that those magnetic nanoparticles are kind of attaching to a cell that you want to separate, and then you can separate the cells in a magnetic field. And you see here an order of magnitude higher efficiency of cell recovery was reported in this particular case. So magnetic nanoparticles. Then in heat transfer. Now heat transfer is also a very important part of process intensification. And the first example that I would like to bring is how thermal conductivity of the material can influence the process. You see here hex reactors. So heat exchanger reactors, it is quite already standard development within process intensification. These are the reactors that look more or less like a plate heat exchangers, and the only difference is that they function as reactors. And the usual construction materials for these reactors are glass or stainless steel. They offer obviously much higher heat transfer rates than any kind of standard reactor like tubular reactor or stir tank reactor. But a few years ago, the researchers started looking into further development in this area by changing the constructional material and replacing this glass or stainless steel with silicon carbide. And if you look into this table above, you see that silicon carbide has a thermal conductivity, which matters in this case. So thermal conductivity through the plates is really an important factor here. And thermal conductivity of silicon carbide is at least 1 order of magnitude higher than steel and more than 2 orders of magnitude higher than glass. So it's a very highly conductive material. So what happens is that when you look into this green table is that the specific heat transfer coefficient overall increased from 660 for Corning reactor, which is made of glass, to around 10,000. If you multiply it by the available area for the mass transfer, you end up in kind of performance factor 20,000, which is again more than an order of magnitude higher than the glass reactor. So just by changing this material, you can improve even further the functioning of the already intensified device. Thermal conductivity, another example, aluminum foam reactor packing. So we speak about improving thermal conductivity within the bed. When you compare it to standard aluminum oxide particles, is about 650 times higher thermal conductivity, which results in absence of a thermal runaway, at least danger of possibility in the system. Yeah, responsiveness to magnetic field. This is something also new and a hot topic, magnetite nanofluids. You could also increase the heat transfer rates by using those type of fluids in your processes. Here, the example shown is about 4-fold enhancement of the Nusselt number or heat transfer. You see here in this graph below. Okay. Responsiveness to microwave field, again, you see materials that can be used also for heating, very fast heating. And an example here is we see petalite composite with iron oxide, and it is compared to a petalite without iron oxide. So in one sense, the iron oxide makes this petalite responsive to microwave heating. And when you see the heating curves, temperature versus time, this is petalite without iron oxide. And the more iron oxide you get in this material, you can have a very, very fast heating. So if your target is heat up very quickly, you can do this with such a material. Super wettability comes again here in different form. That's a super hydrophilic materials that can increase heat flux in the pool boiling. In this case, this is a titania coating, super hydrophilic titania coating that, as you see, the difference is enormous between the coating and non-coated packings. Right. Momentum transfer. In this area, materials intensifying momentum transfer are mostly materials that offer pressure drop reduction, drag reduction. And the properties that we look into is elongational viscosity or molecular stretching, like polymer additives. And this is something that happens already in practice. In oil industry, you see use of the drag reducing either polymers or surfactants. And the figures that they are reported 60, 70, 80%, here 40%. So speak about a very significant reduction in drag. Super wettability. So now we are not adding anything to the process liquid, but we rather coat things. So you see here super hydrophobic microporous Teflon coating that was brought on the on the microchannel, in a microreactor, and this resulted in about 75% drag reduction in water flow through the channel. So just by covering channel walls, you can also achieve a spectacular drag reduction. The same property characterizes another interesting coating type. This is a coating that is made of what they call nanofur polycarbonate, and this is kind of nature-inspired kind of coating. You see here, this is really looks like a fur, and again, the channels can be coated with this. And what is the idea here is that this fur kind of coating entrapped bubbles, air bubbles, when liquid is flowing, and then it allows for lower drag, lower pressure drop. So 50% lower pressure drop was reported for this particular coating. Magnetic field, also in the momentum transfer issues, especially in micromixers. You know, micromixers, we can do the micromixing just in a passive way by just kind of forming of micromixer channels and mixing two or more fluids in there. But we can do it also in what they call an active micromixing by using external fields, external energy fields. It can be acoustic field, it can be electric field. In this case, this is a magnetic field when in the mixing liquid ferrofluid, nanofluid containing iron oxide nanoparticles was added, and the shortening of the mixing glass was about 6-fold in this case, just by using this ferrofluid here. So far, I just brought to you a number of examples of how materials, advanced materials, could intensify different aspects of chemical processes. But the relation between materials and process intensification is kind of resembling, you know, the yin-yang philosophy, Chinese philosophy, about these two elements that are opposing each other, but they are complementing each other, in fact. And this is kind of a relation that I see between materials and process intensification. So materials for PI, but now I'd like to talk about PI for materials, because this is as well important as materials. What can materials do for PI? So in order to do it, I just briefly bring you to our paper that we wrote with Tom van Herven, now professor in Leuven. He was a postdoc in my group at that time, 2009. We wrote this paper on the 100th anniversary of Industrial Engineering Chemistry Research Journal about structure, energy, synergy, and time, where we looked into process intensification through the perspective of 4 domains. The spatial domain. The spatial domain is a structure, basically how you structure your equipment. The energetic domain, the thermodynamic domain, when we looked into different forms of energy that can be used to intensify processes. Then the functional domain, which is basically about the synergy, about how to combine functions in your processes. And obviously the last one is temporal domain, where you think how you can manipulate the time, or can you introduce, for instance, oscillatory elements, periodical elements into your systems. And so this paper was in 2009, and last year the book finally, after a lot of work, the book on fundamentals of process intensification appeared at Wiley, that addresses exactly this issue. So what I'd like now to show you is how these domains of process intensification can address making advanced materials. So you see here, for instance, in a structure domain, some of the technologies that belong to this domain are like microreactors or millireactors, or static mixers even, very old technology you could say, but this is a formidable example of process intensifying device, structured. All these devices are reported in literature and many papers for producing things like polymers, hydrogels, crystals and polymers and nanoparticles. So structure can be definitely used to produce advanced materials. On the energy part, we see things like electric field that are used to make biopolymers. Obviously, microwaves is reported in many syntheses of different materials, starting from polymeric materials through ceramic glasses, composites, carbon nanotubes, graphenes, quantum dots. Microwaves are there. Plasmas, on the other hand, biomaterials can be produced with plasmas. Carbon nanotubes are reported with plasmas. So these are all things that in energy domain. But not only that, you see light, obviously, as a part of energy domain, and photo-based processes, light-based processes are reported for making polymers, hydrogels, colloids, structured biomaterials, carbon nanotubes. Then acoustic fields, ultrasound, polymer nanocomposites, hydrogels, nanobiomaterials, graphene can be made with ultrasound. And then also energy, you know very well, those rotating high gravity equipment, rotating packet beds, spinning disk reactors, they are both used, for instance, in making, polymers or nanoparticles. So as you see, this energy domain offers a lot of possibilities for synthesizing new materials. In a synergy domain, as I said, synergy is something that is symbolized here. So it's a combination or integration of functionalities in the process. For instance, reactive extrusion, very well-known operation used to make polymers. Those hex reactors that I mentioned before can also be used for making polymers. Or another example here is membrane crystallization. Instead of cooling crystallization or instead of evaporating things, you can use membrane to control the polymers and make very nice pharmaceutical crystals. And in time, many things can be also considered for producing those materials, like oscillatory flow reactor and development that came from the group in Professor Xiong-Wei Ni in Edinburgh. They can be made used to make polymers or crystalline materials. Pulse plasma for making nanoparticles, or pulse laser as well for making nanoparticles, thin film materials. There is enormous diversity of the intensified technologies that could be made in producing materials. So now I'm slowly reaching the end of my talk, and a few slides summarizing of what I said. I think that you could see in this material that I presented that advanced materials present really an important third way of intensifying processes. The point is that they carry both main ingredients of PI, which is first of all the innovative character and the magnitude of effects achieved. So when we look back into this the year 2000 paper, in which we introduced this process intensification as consisting of equipment, the hardware part, and the soft part, the methods, I think that the time is now to make a triangle out of this and to introduce materials to this kind of toolbox. And materials should be given a place in this field that they really fully deserve. As you saw in my presentation, I presented many materials, but only few of them have been seen in industrial scale applications. For instance, you know that zeolites are quite popular and are used in catalytic reactors, in mass transfer processes. Silicon carbide is used in distillation columns, or those drug-reducing polymers in petroleum pipelines. But most of these materials have not been produced on industrial scale yet. So there's a problem, and obviously the hurdles need to be overtaken, and these hurdles, first of all, include the cost, but also in many cases, the lack of large-scale manufacturing technologies for those materials. So my last conclusion is that we expect that this yin-yang relation between materials process industrialization will also help to overtake those hurdles, and we will be able to develop low-cost process industrialization-based technologies for manufacturing those materials that are now either impossible to manufacture with current technologies or very difficult to manufacture. So I think there is a very interesting opportunity for process intensification in advanced materials. So having said that, I'd like to refer you to the paper that appeared 10 years after this previous paper on the 110th anniversary on industrial engineering chemistry research, the paper that I wrote together with Peng Yan, currently in Tianjin University in China, on the missing link between materials and process industrialization. In that paper, you will be able to read much more of the material that I briefly presented at this conference. And I thank you very much for your attention. I'm available for any questions you might have. Thank you.
Okay, thank you very much for your amazing lecture. Now we continue to discussion session. So please the committee to show the question from the chat room. Okay, Prof. Stankiewicz, as you can see here, the first question comes from Griffin. Could you give us some examples of process intensification or material advancement that has been commercialized in industry?
Yeah, so well, of process intensification as such, I could give you many examples of things that already are on industrial scale, but this would require a separate lecture on the industrial advancement in process intensification. But you see, starting from microreactors up to the huge things like reactive distillation, divided wall columns, and so forth. There are many things, but particularly related to material advancement. So this question relates to my last slide, where I said, you know, there are only few examples of advanced materials that were used, that are produced on industrial scale, and they can that can intensify processes. I brought the zeolites example, I brought the silicon carbide example, or those polymers for drug reduction. So there are not many, and this gives a perfect opportunity to use new intensified technologies to broaden the range of the materials, advanced materials. Yes.
Okay, and then the next questions so comes from Mr. Kurniawan. How to do the scaling up the microreactor? As we know, the changing of the dimension of microreactor significantly influence the mass transfer and fluid dynamic on the microreactor system.
Yeah, that's not directly related to the advanced materials, but the microreactor. We discussed this issue also in the book that I showed you. For microreactors, actually there are two ways of bringing this to a larger capacities. We don't scale them up, because scale up means you change the characteristic dimensions, and we do not want to change any characteristic dimensions in the system to leave it as a microreactor. So we scale it out, yeah, or some people say numbering up. I'm sorry for this probable sound that you hear, but there is a big passenger plane flying over my house, so it will last for a few seconds and it will disappear. So So coming to the microreactors, you can do such as internal numbering up or external numbering up. These are the basic two strategies. The external numbering up means that you have a small microreactor units and you multiply them, just making a big network of those units in parallel or in serial. The internal numbering up means that you have a micro channels, but you make one big unit by multiplying the plates, the platelets in which those micro channels are. A typical example of this scale of the scale out in terms of internal numbering up are reactors developed at company Velocis for Fischer-Tropsch synthesis. They have quite big microreactors that contain hundreds, if not thousands, of platelets with those micro. So there are two basic ways. The first one, the numbering up external, is maybe applicable to very small production scales, but it is complicated and complex in terms of instrumentations, because you have to provide each of these single modules, single small microreactors with a control equipment. Yeah, so that's a problem there.
Okay, thank you. And then the next question, please. This question is from Mr. Kusumo Cahyo. Prof. Stankiewicz, how deep...
That's a very good question. I read it from my screen.
Okay,
how deep should material science subjects introduce to bachelor students of chemical engineering? Well, I must say that in 1977, when I graduated from Warsaw, I had already a material science course in my curriculum. Obviously, this was a different type of course. This was a course related, as I said, to this construction of materials for equipment. But in general, I think that this is a very important issue to introduce materials to chemical engineering students. I'm not sure whether it should be done at the BSc level or rather at the MSc level, but definitely this needs to be addressed for the future.
Yes, I fully agree. Okay, next question, please. Okay, so this is from Evander. With the recent rapid development of advanced materials such as CNT, do you think supercapacitor can be used as a feasible alternative to EV?
Well, this question reaches far beyond my expertise. So I'm still, chemical engineer, and with the process intensification, I have very little knowledge of the batteries and generally the energy storage thing. So I have to skip this question. I don't want to give an answer that could be wrong.
Okay, so sorry, Mr. Evander. And then the next question is from Abdur Rashid. What is the most interesting finding that you have encountered about the advanced materials throughout your year as researcher?
Well. What were the most interesting things? Well, I worked for many years in Delft with materials that are responsive to microwaves. My research for the past 15 years was around using electricity-based technologies for running processes. So instead of standard reactors that are using heat from steam boilers, for instance, we were using the electricity either in the form of the microwaves or in the form of plasmas or in the forms of light, photoreactors. And I think that the most interesting findings were connected to the catalytic materials that we developed to work with microwaves. What is important in this material is that you can see that if you have a catalyst with a nanoparticles of metal, of the catalyst, the absorption of microwave is kind of proportional to the amount of these nanoparticles in the catalyst. So these nanoparticles get the energy preferentially, much quicker than the support, which is usually alumina or something like that. So in this sense, we started thinking that maybe you can bring the energy exactly to those nanoparticles by using microwaves instead of preheating the whole feed in the reactor. So you bring the cold stream into the reactor and you only irradiate those nanoparticles, and then you get much better selectivity. And this works, really. This works. You can see the paper from University of Zaragoza in Nature Catalysis, I think, from last year, where they proved really on a very small scale how it works. Yeah. So this was something that kept me really awake in terms of materials in the last years.
Okay, thank you. The next question. So as you can see here from the chat room, from Mr. Guntur, as you mentioned, one of the important aspects for process intensification is being creative. Can you give some tips on this? What is the fundamental or approach we should take in order to find intensification potential?
Yeah. Well, that's a very good question. I agree that the creativity is an important aspect of PI. And the tip that I would like to give you is the tip of educational nature. And namely, we have been carrying out teaching in process intensification at master level for about almost 20 years now in Delft. And the course contains the lectures, obviously, on various types of technologies, various approaches, but also contains a project that the students are expected to use their creativity to intensify an existing process. And the standard process that we've been using in our course is the carbaryl process of Union Carbide in Bhopal. And many of you know how it ended up with a horrible tragedy with thousands of people killed. And we give this assignment to the students after they have heard the lectures, and say, okay, you have a now basic knowledge, and now use your creativity to redesign the Bhopal plant in order to make it intrinsically safe and sustainable in this sense. So I think and then in this process, we supervise kind of brainstorming sessions in which the students generate the ideas. They have to generate the ideas on how to improve the process. It's not only Bhopal, we have a kind of library of these processes, depending on the number of students participating. But we supervise their in this idea generation sessions, and they need to converge, they need to screen these generated ideas, they need to assess the feasibility of the ideas, and then bring some new concept of the process. So this is the way we are doing, and I think this is a good way to do.
Okay, thank you. Is there any other questions from the participant? So you mentioned there are 4 domains concerning thermodynamic, functional, spatial, and also time. Does it mean that in terms of re-engineering, the kinetic aspect will still become the determining step?
The kinetics.
Yes.
So, well, you see, this is the big question also for process intensification, because many years ago we looked at the process intensification as I'm sorry, as the thing that can only kind of remove mass transfer limitations or heat transfer limitations, that kind of stuff. But if you look into, and this was an eye-opener for me personally, I at one point I looked at the very fundamental literature on chemical physics coming from the University of Stanford when they intensified kinetics of the reaction, intrinsic kinetic of the reaction by using the laser energy. And this was about reacting chlorine with a methane molecule. Traditionally, these two molecules, in order to react, they have to collide frontally with large energy, and they produce obviously the hydrogen chloride. But they irradiated the methane molecules with a laser light of certain frequency to make a resonant vibration of the CH carbon hydrogen bonds in the molecule of methane, and the other kind of collision became effective, namely the hydrogen molecules were hitting on a site, like a site collision, and they were, the molecules of methane became bigger because they were vibrating much more with this laser light, so they became easier targets for the hit. And in this sense, the kinetics increased by more than 100 times of the same reaction without using temperature. So macroscopically, temperature was not used. So in that particular moment, I said, yeah, this is also an intensification. You can influence kinetics of the reaction. Obviously, this is a fundamental research. It will probably never happen in industry, but it shows, that kinetics can also be addressed.
Yes. Okay. Is there another question? Yeah, okay. At the end of your presentation, you presented the triangle: equipment, methods, and also materials.
Mm-hmm.
Does it mean that the definition of process intensification would change?
What will change?
The definition. The
definition. Yeah, I think so. Yeah, I mean, at least from now on, how I see process intensification, it includes the materials, definitely. There are many definitions. I don't want to go into the discussion on definition of process intensification, because many people are working on this, and almost everyone has some own definition of this field.
Yeah.
So I stick to a very simple definition that once my British colleagues have coined, using much less to produce much more, and you can substitute for less whatever time, energy, material, and more. It's about really an orders of magnitudes or factors. So yeah, and materials are there for me, at least personally. Materials are there now. Yeah.
Yeah. Okay. Thank you very much. Yeah. So I think because the time limitation, we must conclude our discussion session. So thank you very much, Prof. Stankiewicz.
My pleasure. Have a nice day further, or nice evening, I should say. Thank you very much. See you next time.
Token of our appreciation for your time and valuable contribution, we can present a certificate for you.
Oh, great. Thanks a lot. It will be a pleasure to have this certificate. Thanks a lot.
Okay, welcome.
Thank you.
Thank you.
So once again, we sincerely thanks for your amazing lecture today.
Oh, yeah.
Okay, ladies and gentlemen, I think I thank you very much for your active participation in this conference. With this session, we conclude our second plenary lecture. I hope you enjoy the programs. Thank you very much, and I conclude my duty here as the moderator. So thank you very much, and stay healthy and safe. Thank you.
Thank you very much to Dr. Budi and our distinguished speakers. This question was very insightful and also very interesting, and hopefully it can motivate all of us who join this event to continuously advance our industry. Now, as a token of gratitude, I would like to invite Professor Setiadi to give a certificate to Dr. Budi for being the moderator of today's plenary session. And maybe the committee can take a picture of it too. Okay, please, Professor Setiadi.
Okay, we just like to thank you to Yogi to be a moderator for this plenary speaker for plenary session. Thank you, Yogi. Thank you very much.
Thank you very much.
Okay, thank you very much to Professor Setiadi dan Dr. Budi. And now I would like to invite all the speakers, moderator, and also all participants to take a picture together. If you don't mind, please turn on your camera. Please, everyone. The committee, can you give us a cue? Okay. Is there anybody who can take a picture?
Okay, I will take the picture. So everybody smile in 3, 2, 1, smile. Okay, once again, 3, 2, 1, cheers. Okay, that's a wonderful picture.
Okay, thank you so much to all participants. And now I would like to invite Professor Chandra Setiadi as the chairman of STKSR-Symphosis 2020 to give closing remarks. Professor Setiadi, time is yours. I'm sorry, Professor. Yeah, the mic is not unmuted.
Okay.
Okay, thank you.
Okay, good afternoon, ladies and gentlemen. It may be still morning in the Europe. I believe during these 2 days, all of us have obtained a fruitful discussion. So in this STKSR 2020, in conjunction with the Symposium on Photocatalysis and Photocatalysis, with the main theme, as we know, it is circular economy for a better world. We have learned a lot from the keynote session delivered by the amazing keynote speakers and also invited speakers and the parallel sessions. Once again, on behalf of the committee, I would like to thank you all for delivering very interesting and important subjects to all of us. Then we can deepen our knowledge. Furthermore, I would like also to thank to the sponsors and also to the IT directors to make this conference a success. So I sincerely hope that all these conferences or all the presentation or discussion contribute to solving our problems in our countries and also in the other part of the world. Although our contribution may be small, but it's still valuable to our society. Although this is the last day of our conference, so the conference, our networking, it's not over yet. So we will communicate one to the others, although it is we dance virtually, but hopefully we make a networking, and then we will collaborate in the future. And also for some of you, for the participants, regarding the papers, it might be some of the paper will be selected and then submitted to the suitable journals. However, we cannot guarantee that your papers will be published by the journals, because the final decision will be decided by the journal in themselves. And also the waiting time, it might be various from one journal to the others. So we kindly ask for your patience about the journal publication. But the last but not the least, I would like to thank to all of you. Thank you once again to the sponsor, to the scientific committee members, to the committee, organizing committee members, and also to the students. Having made this conference is a success. See you again in the coming conference. Hopefully it is in the better way, in the better situation, and we can meet each one with the others physically, and stay safe and keep healthy. Thank you. See you again probably in the next 2 years. Thank you.
Thank you very much, Professor Tiadi, for your wonderful remarks. And now, before closing the event, the committee will have a closing video. Please do not leave the Zoom meeting yet. Wow, that was a very nice video. And I would like to congratulate Dr. Jenny Rizkiana for being the chairman of STKSR 2022. Once again, I would like to thank our sponsor and supporters for helping this event to come true. The 2020 STKSR-Symphosis is sponsored by PT Energi Manajemen Indonesia Persero, Kurita Water and Environment Foundation, and PT Rekayasa Industri. Ladies and gentlemen, now we have come to the end of the second day of the main event of 2020 STKSR-Symphosis Virtual Conference. On behalf of 2020 STKSR-Symphosis Committee, I would like to express my utmost gratitude to all those who have supported this event and to the all distinguished speakers and participants for your kind attendance and active engagement during all the event of this year's STKSR. I would also like to apologize for any inconvenience throughout the event. See you at the 2022 STKSR. Bye-bye.
Okay, thank you all. Bye-bye.